Hello and welcome to my presentation for the IBM Capstone project. My name is Harald, and as requested, here I am. I'm gonna present to you my findings and my approach. My project or my presentation is divided into two parts, where the first part is for the stakeholders, so things will be very basic over there, and the second part is for my data science colleagues, where I'll try to get a little bit more in depth about the whole approach. So have fun. Okay, my project was called Win Prediction for Soccer Games, and let's see what the use case is over here. So assume somebody approaches me and asks me or tells me that they want to assess betting quotas for soccer games, and this whole thing should be based on a quantitative approach, meaning that team A plays versus team B, and there is a 70% probability that team A wins, a 15% probability that it's a tie, and a 15% probability that team A will lose. So somehow the quotas, or somehow this fact should flow into the quotas, meaning that 70% should be, of course, the inverse times 0.3, and so on and so on. And they don't know if it's possible. They want to see if this is even possible. So I should deliver them a proof of concept. So it should be not a finished data product, but only they want only to see if it's possible. Okay, so fellow stakeholders, let's have a look at the data. We have a game database which I scraped from the internet, from transfermarkt.de. That's an internet page where you can find all football history. And I scraped all the games from the Bundesliga, which is the German league, La Liga, the Spanish league, Premier League, from 4 years, from the 4 past years. And yes, we have many games, where one game is comprised of course of team A versus team B and the score. There one team is two teams are comprised of 11 players, so player 1 to player 11, and one player of course has many attributes. So how much is he worth, how good can he shoot, how high can he jump, and so on and so on. Now the question is, where do I find these attributes? And for that I chose the FIFA 19 database, which gives me these attributes from about 18,000 soccer players, and every player has about 88 attributes. So from this I built the team, and from the team I built one game, and from the score and the game data I can train a supervised model, which then helps me to predict the outcome. And let's look at the model performance and the results. I trained a neural network, or 2 neural networks. The first one showed these results. They don't look that good. They're slightly above chance level. So we see for tie we are at chance level, but for win team A and win team B, we see that we are above chance level. So it's I am able to tell at 50% chance if a team will win or not, or if the other team will win or not, which, well, if you play it smart, you can work that into the betting quotas. The second approach with another neural net wasn't that good. We see that it didn't take into account the tie class, meaning that a game, it always classified a game into win A or win B, which is definitely not good. And as a third approach, I trained a support vector machine, and we see that the first net and the support vector machine show pretty much the same results. So what we can tell from this is that the second net is not good, and it's indifferent which of the other two approaches you choose. However, keep in mind that the results are not that good. So what I would say is that the factor of luck or randomness, which is inherent to a soccer game, prevents from really telling if some team wins or loses from a quantitative approach. So how did I do this? This part of the presentation now goes to you, my fellow data scientists. Let's have a look at the data in depth. So to crawl the internet, I used the Selenium package for Python. All the work in general was done in Python, and for data manipulation and the whole thing, I used Pandas, NumPy, then Matplotlib and Seaborn to look at the data for data exploration. And the FIFA 19 database gave me 88 attributes for each player, which is way too much. And so I decided to throw out all the strings, all the string attributes like photo and nationality and flag. They don't give me any information. So I was left with 44 attributes, where 42 are numerical and the last two are the value and I think the contract. No, their wage was still a string, which with this code snippet over here, I casted it to integer values, so that now I have 44 attributes, which are, what is a problem, very, very highly correlated, as you see here. So the whole correlation matrix shows many correlations above 0.6, which is way too much. So what I did, what I proceeded to do with scikit-learn, Pandas, and NumPy was to do a PCA on these 44 attributes, and we see here the principal component the principal components and how much of the variance from the whole data they explain. And I took a subjective threshold of 1% to throw away excess principal components. So only components were taken into account which explained more than 1% of the variance, and I remained with 8 features. So the complete data set looked like this. I had 3,510 games after data cleansing, of course, which that's the first dimension of the matrix, and 2 times the team features. So one team has 8 features, times 2 is 16 features, where one team vector was built like this. So I just took the mean of all the player attributes. To train the model, or I chose 3 different models, as you've seen. I used Keras with a functional API and scikit-learn. Of course, I split into training and test size, 70-30%, and the train set then was again split into train set and validation set. For my neural networks, I used the Adam optimizer with a learning rate of 0.001, and as a loss function, I used a categorical cross entropy. So the first model, the second model also a neural net, and the third model was a support vector machine. The first model looked like this. It had 3 hidden layers, which were all fully connected, so dense layers. The first 2 had 10 neurons with activation function ReLU, and I initialized the weights as a he, which is kind of Xavier initializer. Yes, and the prediction or the output layer is this one, win A, tie, or win B. The second model looked like this. So I had 2 inputs, 1 input for team A, 1 input for team B. There I congregated the team vectors, then concatenated them, gave them into another hidden layer, and the prediction layers again down here. And the support vector machine, okay, this is a very easy visualization of it. Of course, this is in higher dimension, but it tried to bring a decision functions so that I have these three classes: win, tie, or win B. This, of course, is the optimal case, which again was not that good. My results were not that good. Yeah, so I see I'm slightly over the time. My results and metrics. I used scikit-learn for that, and it's pretty straightforward for classification problems. I just took the accuracy, precision, recall, F1 score, and confusion matrix, as you saw in the stakeholders presentation. So this is pretty straightforward and standard for classification problems. Yes, and for the problems in hardship, I don't want to bug you with that and the Outlook. If you're interested in it, just have a look at my GitHub and the model deployment doc where I documented this. Okay, thank you very much. I hope it was slightly interesting, and yeah, have fun. Cheers.